recording real quick?
Okay. I clicked something. Okay, there we go. All right. So as I was just introduced, my name's Tucker Irvin. I'm a PhD student at the University of Alabama. And today I just kind of want to talk about permutations whose reverse shares the same recording tableau in the RSK correspondence. And I first want to just thank the organizers for putting this together. It's really nice to have a student seminar I can attend online and see a whole bunch of different topics, especially since I've only really gotten into combinatorics in the past year or so, and it's really neat to be able to access something like that. So with that out of the way, I kind of just want to hit y'all with the main idea of this talk. And really what we're trying to do is we're trying to count permutations that are fixed under some certain simple operations. That's really the heart and soul of what we're doing. We're just saying this permutation goes to this thing, and if we apply an operation to this permutation, it goes to another thing. How can we relate those two? And if we can relate those two, how many of those are related in that way? And this is really a joint work with, let's see, 5 student co-authors and my advisor. So we have Blake Jackson, Jay Lane, Jack O'Donohue, Sun Nguyen, and Michael Vaughn, who were all the student co-authors. And we have my advisor, Kyung Young Lee, who we also wrote this paper with. It's posted on the archive if you want to look at it. But the way I kind of want to introduce the background to how it came about. So last semester, my advisor decided that he wanted to offer a combinatorics course to his students and the graduate department as a whole, so that we would just have a better background in combinatorics, because combinatorics shows up in cluster algebras a lot, and he really kind of wants to develop more tools to apply to those. So we started this combinatorics course. We were using J.L. Martin's combinatorics notes, really great set of online notes that he uses to teach. I highly recommend going through them for reference or just learn about any little thing. And so we got through the semester, learned about posetsets, matroids, all that fun stuff. Halfway through, he walks in, says, here's an open problem in the exercises of these notes. And here's an open problem in the exercises of these notes. Let's solve it. And a couple months later, we finished the course. We finished the semester. We had the bare bones of the solution. Over the summer, we finished it completely. It's posted on the archive, and we're looking for a journal to publish it now. So it was pretty great topics course, in my opinion. It ends with a paper. So, sorry, it's a fun tale. So what we're going to do is, since this is really my first formal introduction to combinatorics, it's kind of a self-contained talk. So I'll just start with like one-line notation of permutations and build up the RSK correspondence. And then I'll talk about how we can count these things and then how we arrive at the main result. So to begin with, we have 2 things that we say about permutations, and those 2 things basically about boil down to one thing, and that is the one-line notation. So permutation in integers, we send 1 to W1, 2 to W2, so on and so on until we get n to Wn. And to write it in one-line notation, we just take the bottom sequence of this permutation and write it. It's really compact notation, makes calculations easy, really makes it easy to write it in line. So you don't have to build a new line or do a whole bunch of cycles that kind of break away from the text. It's just right there. And so as an example, if we had the permutation that sent 1 to 5 fixes 2 and 3, sends 4 to 1 and 5 to 4. For the one line notation, we just write it 5, 2, 3, 1, 4. Really simple. That's probably one of the greatest things I learned in the combinatorics class, was that I can write permutations like this, save me hours worth of work. And then you have the kind of uglier cycle notation right next to it. So this then leads us to the second thing we're going to say about permutations, which is that we can apply 3 basic operations. One is the inverse permutation, which is just the group theory inverse, kind of standard stuff. And then we also have the reverse and the complement permutations. So if we had written W as W1, W2, so on to Wn, the reverse permutation is you just write it backwards. Wn, Wn minus 1, so on to W1. The complement permutation, same kind of idea. Each entry, we subtract each entry from n plus 1, and that gives us the complement integer in that in the set 1 to n. So the integer wi and its complement sum to n plus 1. So they're complements of each other. So these are the 3 basic operations we can consider, and we can consider combinations of these operations, performing one after the other, and so on and so on. And there's really only one other one that we kind of need to explicitly define, which is the reverse complement permutation, which is just you do the reverse and then the complement, or the complement, then the reverse. They commute with each other. And these are kind of the simple operations that we're looking to see if these permutations are fixed by. Well, the RSK correspondence, it takes in these permutations and it spits out some other stuff that is going to get fixed by these operations. So as an example, we're running with W equals 5, 2, 3, 1, 4 throughout the entire talk, just because that one's in the set we're looking at. And so it's a really nice one to play with. So the reverse of W, you just write it backwards, 4, 1, 3, 2, 5. The complement of W, you apply the process, you get 1, 4, 3, 5, 2. And if you apply both processes, you get 2, 5, 3, 4, 1. So this one line notation really makes these reverse complement and reverse complement operations easy to compute. You can also think of them as multiplication by a certain involution, but that requires thinking about multiplication in the group, and we really don't want to do that for this. Okay, so we know what the RSK correspondence takes in. It takes in these permutations in one line notation, and it spits out some other stuff. So we're going to talk about the other stuff now. And really what they are is just Young diagrams. So if we have a partition of n, which is just a weekly decreasing sequence of integers that if we sum them all together, we get n, we can form a Young diagram associated to that partition. And what that does is that all we have to do is we just take each entry of the partition and we write down that number of blocks. So for this one right here, for this one right here, we start with 5 and then we go, so we put down 5 blocks and then we have 4, so 4 blocks, 2 blocks, 2 blocks, 1 block. It's basically a left justified upside down staircase, so to speak. You can have a couple versions where they're like right justified or left justified staircase going up, but this is the English notation. The other one is called the French notation. So with that out of the way, since the partition, the integers of the partition sum up to n, we get n blocks in the final Young diagram. So we could fill each block with an entry from 1 to n. And so there's a special way to do that that we call a standard Young tableau. And it's really just a filling of the Young diagram of shape lambda. So with the numbers from 1 to n. So the rows increase from left to right and the columns increase from top to bottom and strictly increase. So it's probably best to just look at an example real quick. So for the shape lambda equals 3, 2, we get a Young diagram. It's 3 boxes on top and then 2 boxes for the second row. And then we can fill it with exactly 5 fillings that satisfy these properties. Each one, the rows increase from left to right, the columns increase from top to bottom. And so we have this bit of notation that's called F lambda, F raised to the power of lambda. And that just represents the number of standard Young tableau of that shape. So count the fillings, it gives us this nice number. The bigger n gets, the bigger F lambda can be. For example, for this lambda, there's something like 60,000 fillings for that shape alone. So it can get really big really quickly, which is just a little kind of aside. Okay, so going back to the RSK correspondence, takes in these permutations and it's going to spit out pairs of these standard Young tableau. So for each permutation, we get a pair of standard Young tableau of the same shape. And it's really nice because it's a bijective correspondence. Full name is Robinson Shinstead Knuth correspondence. Everyone just calls it RSK because it's like 10 syllables. And we get this bijective correspondence between permutations on n letters and pairs of standard tableau of shape lambda that are partitions of n. So we get every permutation, we get 2 really nice tableau of the same shape. And the heart and soul, well, Robinson first defined this correspondence like 100 years ago or so. Then Shinstead came along and cleaned it up a little bit with his insertion algorithm. It's really the main way to do it, though there are probably 30 different ways to define this correspondence. And Knuth just added on to these things. And so that's why all 3 of them are in the correspondence, but we really kind of algorithm for now. And so what it does is if we have an empty tableau and we take an integer x, then all we do is we just add the x into a single box. And if t is not empty, we check to see if x is greater than u for all entries u in the top row of t. If it is, we append x to the top row. So we just slap it on the end right there. And if it's not, it bumps the first entry it's less than. So if it's less than u, it takes the place of u, and then u goes down and you apply the same idea to the second row and the third row and so on and so on. And so what you do is you just do this until the bumping stops for whatever integer you gave it. And so this allows us to explicitly define the RSK correspondence. So if we have a permutation written in 1-line notation, what we do is for our first tableau, we just apply the Shinstead insertion algorithm to that sequence of integers given by the permutation. So we do it to W1, then do W2 to that, then W3, so on until we get to Wn. Naturally, we call P of W the insertion algorithm. Oh, not the insertion algorithm, the insertion tableau. And with that, once we have that, we record where each new cell was created. So whenever a new box appears, we put that same box in the Q tableau and fill it with the step that we are on. So if a new cell appears at step 1, we fill it with 1. If a new cell appears at step n, we fill it with n. And naturally, this gives us that Q is the recording tableau. It's the nice name. So we have the insertion tableau, which is P, and the recording tableau, which is Q. I'll probably mix these up somewhere, so just try to keep that in mind. And what is really helpful is just to see this algorithm in action. So let's see if I can get the annotation tools to work today. There we are. So we start with an empty tableau P, and if we're working with RSK of 52314, we add 5 first because that's the first entry we get. So it's just a box with 5, and the recording tableau, the first box is created. We just add a 1 to it. The next integer is going to be 2. 2 is less than 5, so it has to bump it. So 2 occupies this spot, and 5 goes down here. The cell that is occupied by 5 is the second one created, so 2 appears in the recording tableau. And we kind of just keep repeating this process. So we have 3 is greater than 2, slapped on to the end of row 1. 3 fills this new cell. 1 is the next one, bumps 2, 2 bumps 5. So 4 has to occupy this cell. And then finally 4 appends to row 1. So we get a 5 there. So really nice algorithm. Once we plug it in, once we finish the algorithm, we get the insertion tableau and the recording tableau. Both have the same shape. And so they're pretty nice. And then we just have to define one more map before we can go on to what we're counting. And that's really the evacuation map. It's an involution which takes any standard Young tableau to another standard Young tableau of the same shape. So if we have a standard Young tableau Q, it's going to spit out, we apply evacuation to it, it's going to spit out some other tableau P that is the same shape. And if we apply it to P, it's going to spit out Q. Really, really nice stuff that relies on this kind of concept of the delta operator, which we're not going to go into. But it basically, a cell of the evacuation of Q is going to contain n minus I if that cell was vacated when passing from delta I to delta I plus 1 of Q, where this operation just deletes the minimal element of the tableau and slides the rest of the entries over to fill the gap created. And that's, you may have heard of it, it's called Judidakin. I practice pronouncing that quite often. It's the sliding game in French. So it's kind of like those, if you've seen those puzzles where it's just a square filled with a bunch of squares that you can slide around, it's exactly that concept just applied to this kind of tableau shape. And it makes more sense if we go through it. So if we apply this idea to Q of 52314, which we calculated last time as 13524. 1 is the minimal element here. So if we apply delta to that, we just erase that, and then we move 2 up and 4 up. And we do that because 2 is less than 3. You just go towards the neighboring cell that contains the least element, so to speak. So what that gives you is this eventual tableau, delta Q. We know that this cell right here was vacated, so to speak. So 5 occupies that cell in the evacuation of Q. In here, delta 2, the minimal element is 2. So this is vacated. 3 is less than 4. So this slides over, and this cell is vacated. So 4 occupies it here. 3 is minimal, so 4 slides up. This cell is vacated, occupies here, and so on until you eventually get the evacuation of Q.
I'm sorry, I forgot. Did you say that this was an involution?
Yes, it is an involution.
Okay, because I feel like if I now do this algorithm on what I got out, I'm going to end up with 4 or 5 in my top row.
Let's see. So we delete 1, so this slides over.
Yeah.
So 5 appears here. And then,
oh no, you're right. We delete 2 and 3 slides up. Okay.
Yeah, it's really hard to see from the tableau what the evacuation is going to do. You really do have to work through each individual step, and then it pops out. There's a couple easier definitions of this that are more intuitive, but this is the one that works for everything, and it's more closely resembles the Shinstead algorithm.
Thank you.
Okay, so with that out of the way, we finally have enough machinery to kind of like go over the counting problem we want to talk about. And really, it's kind of a whole set of counting problems that we whittled down to 1. And so here's a really busy slide that I couldn't figure out how to shrink down. So we're just going to work with it. So when you take combinations of the inverse, reverse, and complement operations, what you're going to do is after you've done everything, it's going to reduce to exactly 8 options. Either it's going to be the identity, it's either going to be the complement, the reverse complement, the inverse complement, the inverse reverse, or the inverse reverse complement, which that's a bit of a mouthful, but any combination of the inverse, reverse, and complement operations is going to reduce down to one of these 8. So if we look at what RSK does to these permutations under these 8 operations, then we can kind of see, we can count these things. And this list is known. It was given in a paper that we cited it from. Well, half of it, we just did the other half, which follows just from some relations. So this kind of gives us a question of how many permutations satisfy QW equals QW star, for star being one of these 8 operations. If star is the identity, then that's really easy. That's just all of them. But if it's one of the other 7 ones, then what are we going to do? And the surprising answer is that we can break these down into 5 easy ones and 2 hard ones. And we started with one of the hard ones, not knowing it. And then we found the 5 easy ones after that, and then the other hard one. So the one we started with was the only one that wasn't really solved yet. So we're just going to go through the easy problems real quick, and then we'll get to the hard ones. So we can trivially tackle the recording tableau of W equals the recording tableau of W complement, because then just from our relation, we know that the recording tableau has to equal the recording tableau transposed. And that's never going to work if n is greater than 1, because your elements in this corner, your element in this corner, they're going to be swapped. And since we're working with distinct entries, they're never going to equal. So you can never have a symmetric standard Young tableau. They're always going to be slightly different. So for n greater than 1, this is just going to be a trivial set. So it's going to be completely empty. There's going to be no permutations that satisfy this. The first interesting one we get is when we ask when the recording tableau of W equals the recording tableau of W inverse. And that only happens when Q of W equals P of W. So this requires that W equals W inverse. And it only happens once for each standard Young tableau. So if we sum up all the standard Young tableau, we're going to get the number of elements in the set, and it's going to equal the number of involutions because each involution has to be in the set and vice versa. And that was known for a long time. It shows up in homework problems and books dealing with this. This one wasn't really, we hadn't really seen it in the books, but it's pretty much the same idea as for IN. You just have Q of W equals P of W T instead. And so what that requires is that you're just looking at the number of standard Young tableau that have a symmetric shape. So the filling is not symmetric, but the shape itself is symmetric. So if you just transpose it, it's going to be the same thing. And so that's a really nice kind of conceptual idea of what these things are. And then if you play around with the reverse map, you can show that IN is, equal to IRN, ICN is equal to IRCN, where we're looking at recording tableau fixed by the inverse reverse and the inverse reverse complement, respectively. And so that's as nice as can be. We've done 5 of the 7 already. We're really happy with that. They're done by other people or done just trivially before, but it's nice to have them all laid out. So that leaves us 2 hard counting problems. They're not easy to tackle. They're not trivial in any way. And those are counting the set Rn, which is just the set of permutations which have their recording tableau fixed by the reverse operation, and RCN, which is the same thing but fixed by the reverse complement operation. So one really quick thing to note is that they share the common property of both sets of these permutations do not use the tableau P of W. So P of W could be anything. We only worry about Q of W in this case and the properties of Q of W. If Q of W satisfies either this long property or this property, then any P of W attached to it is going to be a good pair, and that's going to give us a permutation due to the RSK bijection. So by looking at that, we can just count these sets, and we don't have to find a way to think of them as permutations, so to speak. We can look at them solely as tableau. So if we kind of let A lambda be kind of using the same notation as F lambda, if we let A lambda be the number of standard Young tableau of shape lambda that satisfy Q equals the evacuation of Q transpose, and B lambda be the same thing, but without the transpose, then we get an immediate just counting of these, because the F lambda comes from all the PWs, and A lambda is just the number of QWs that satisfy that. So they multiply together, sum up, you're good to go. The really interesting thing that we didn't learn until after we finished RN was that there already exist formulas for the B lambda. It's given in a paper called Canonical Basis and Self-Evacuating Tableau. So when Q equals the evacuation of Q. It's a really kind of nasty formula, so we were hoping to solve it for a easier to use formula, but we haven't been able to finish that yet. But the only thing we couldn't find was a formula for A lambda. And so that really kind of left RN as the only unsolved case. And that's what we did. So if you experimentally tally RN, and that was in J.L. Martin's notes, you get this really strange sequence where whenever n is even, Rn is trivial, and whenever Rn is odd, whenever n is odd, you get this weird sequence of integers. And it turns out, if you look for something to fit it to, it fits 2 to the n minus 1 over 2 times n minus 1 choose n minus 1 over 2 for n equals odd and for n odd and 0 when n is even. And if we can show this, this will polish off the last counting problem and give us a really nice formula for the number of permutations in Rn. And so that's what we set out to do, and thankfully we were able to do so. And I'm kind of walk you through how we arrived at this main result. I'm not going to do the proofs. I'm just going to kind of give you the way we stumbled into it. So we have this map phi12. And we found this early on in our work. It really is quite possibly one of the nicest permutation maps we can think of. It's not a group. This one is not a group homomorphism. But what it is you have a permutation in one line notation. You add 2 to each entry, and you tack a 1 on the beginning and a 2 on the end, which is why we write it phi12. And this is going to produce a permutation on n plus 2 letters. So if we hit our running example with phi12, it's going to produce 1745362. And that really is a nice permutation on n plus 2 letters. We're good to go. And the reason why we were really intrigued by this map is that it has a great property in that it preserves the relative orderings of the permutation entries. So if we had one entry of the permutation was less than another entry of the permutation, then if we look at the image of that entry in the n plus 2 permutation, that order is going to be preserved. And this kind of idea led us to generalize it to a whole family of functions. And these are sort of my babies. I'm really happy they worked out like they did. So I've got the formal definition up here. It's not super important. It is basically the same idea as the phi12 example. You tack A and B onto the ends, and you either fix or you add 1 or 2 to the entries in between. So if we ran through a couple of examples real quick. So if we applied phi17 to 52314, 1 and 7 get tacked on at the ends. 52314, they're all in between 1 and 7. So you just add 1 to each entry and you get a permutation in n plus 2. If you take phi of 5,3, that same permutation, it's the only one that is less than the maximum of the 2 entries minus 1 and greater than the minimum entry is 3. So that one is the only one that gets added 1. The ones below that are fixed, and the ones above that have 2 added. And then you tack on 5,3 at the ends, and that gives you a permutation. Same idea for phi 3,5, except you swap 3 and 5. And so these maps are fantastic, really great. Some of them, one of them is a group homomorphism that like embeds into Sn plus 2. But we didn't really even care about the group structure. All we cared about was that each map preserves relative orderings.
When you mean relative orderings, so could you give us like an example of
Yes.
that? Because there's a couple different things I think you can mean. I'm not sure which one you do.
I may have used like the wrong phrase somewhere along the way. We just mean like, say, you have this entry 3 right here. Well, this corresponds to entry 4.
Okay.
So we know that if we label these W1, W2, W3, so on and so on, we know that W1 is greater than W3, W2 is less than W3,
Okay,
W4 is less than W3, and W5 is greater than W3. And
okay.
if we look at the images of these entries, then this same ordering is going to appear.
Okay, got it. So so the inversions, when you send them through the map, like the less than sign commutes with your map.
Yes.
Okay.
Yeah, I may have mixed up relative ordering with something else. So
No, it's a rational way of doing it. I just wanted to make sure I was on the same page.
okay. We got a little lost in notation somewhere along the way in the previous class. So if I say something wrong, I got lost. I'm sorry. Okay, so that is really the fantastic thing about these VAB maps is that they preserve these orderings. So we can they're basically the same thing. The pre-image and the image are basically the same thing shape-wise, because this shape is determined by these orderings. And that really gives us our next idea, where if QW is symmetric hook-shaped, and again, symmetric just means that the underlying shape, if you transposed it, it'd be the same thing. And hook-shaped just means it's shaped like a hook, so like an L. If the recording tableau of a permutation is symmetric hook shaped, then if you apply a VAB map to that permutation and take the recording tableau of that, then it's going to be either symmetric hook shaped or not symmetric at all. And you really can just prove it by looking at it. So if we take a symmetric hook shape and we rely on the fact that VAB preserves relative orders, is then if you take the recording tableau of VABW, you're going to get exactly one of these four shapes up to transposition. So it's just going to add 2 blocks somewhere in the diagram. And there's only one way you can add the 2 blocks to get a symmetric shape, and that's going to be the symmetric hook shape. And so that just, you can visually see it. And I thought that was really nice thing to pop out from our work. Then, since we have this concept of going up with the hooks, we can go up from SN to SN plus 2. We also kind of want the reverse idea of going down. And we were able to actually do that with one function instead of a family of functions. So we kind of define this theta n, which goes from SN plus 2 down to SN. And what that does is it's basically just, it's pretty much the opposite of the VAB. You forget the ends and you take away stuff from the entries in the middle until you get a permutation on n entries. So if we look at an example, theta 5 of 1634257, you forget the ends and you subtract 1, you get 52314. Apply theta 3 to that permutation, forget the ends, you don't need to subtract anything, it's already a permutation on 3 entries. 231. You do it with theta 1, forget the ends, you subtract 2, you get a permutation on 1 entry. So it's really great. You go up with the VAB maps, you go down with the theta n maps. And that theta n just acts as a left inverse for all VAB. If you compose those two, you're always going to get an identity function. And naturally, theta n also preserves the relative orderings. So that we've defined a family of maps that goes up preserves relative orderings, and we got a map that goes down that also preserves those same orderings. So it's really fantastic, works out great. And we can use that to pretty much once we have that, we pretty much have everything we could want. So if we remember that really big slide, we know that QW equals QWR if and only if QW equals the evacuation of QW transpose. So what that tells us is that the underlying shape of QW must be symmetric. So, and that just follows from the evacuation preserving shape. So we have a symmetric shape for each recording tableau for any permutation W in Rn. So if we use that along with theta n, our lemma on the phi-AB maps, and a bunch of induction, we're able to prove the following theorem. And that's just for all n greater than 1, the set Rn is a subset of all permutations that have symmetric hook shape recording tableau. The subset is often strict. It's strict for every n greater than 5, but that's not really important to what we're thinking about. And while this greatly reduces the RNs, the permutations we have to look at, you wouldn't think this would give us too much, but it actually pretty much completely solves the counting problem. So it immediately gives us that Rn has to be 0 anytime n is even, because you're never going to have a symmetric hook shape on an even number of boxes, because it's always going to be either +1 in the top row or +1 in the first column. And that, quite honestly, a fantastic result. We suspected this from the beginning once we started looking at these permutations, but it wasn't until like the very end of the semester we were able to show this. And it takes like 3 paragraphs to prove, but it's not really interesting to look at. And so once we have that, we can actually just finish off the proof. So if W is a permutation on n entries, then Q of W equals Q of WR if and only if Q of W satisfies the following properties. It has to have a symmetric hook shape, which was that theorem we just saw. And it also satisfies a really kind of strange property that the element I in the first row of QW implies that n minus I plus 2 belongs to the first column of QW for all I in 1 to n with I greater than 1. And that's kind of a weird property that just follows from Q of W equals the evacuation of QW transpose. It's relatively easy to show. It just doesn't, it's not obvious when you look at it. And once we have those two, we immediately have Rn equals 2 to the n minus 1 over 2 multiplied by n minus 1 2's n minus 1 2 when n is odd and 0 when n is even. The binomial coefficient, that's just the number of symmetric hook shapes. And 2 to the n minus 1 over 2 is the number of tableau that satisfies our second property right there. And once that is done, you have everything. You've solved the last counting problem. You can count each one of those sets. Self-conjugate partitions are always in bijection with partitions with the odd number for each part. Yes. And that's pretty much the end of it. So thanks for coming to the talk. I'll be happy to answer any questions.
Let's thank the speaker.
Also have all our references up on the slide. Yeah, I saw
Lecture notes.
Yeah, those were fun to look through.
How many typos did y'all find as y'all were going through them?
He kept updating them as we were going through it, so I'm not sure.
My experience is every time I read through those notes, I find a new typo. But if you tell them about it, then you get an acknowledgement at the beginning of the notes, which is why the acknowledgements are so long.
Yeah, we actually emailed him about it. He thought it was really neat, and he sent us to a bunch of other authors. Like we emailed Stanley and Bruce Sagan about it, and they're like, "Oh, this is cool. I haven't seen it before. It's neat." And so we really enjoyed this problem. It was fun to solve. Reading through the chat now.
I have one question.
Mhm.
You have shown us various counting problems, formulas for them, but are there nice closed formulas like for the last counting problem? So for the number of involutions, there should be a sum of binomial coefficients and some factorial part. But is there something also for the other problems?
That's the thing. Not really. We suspect that there might be. Let me find where they are. We suspect that we might be able to find a closed form for RCN, but I couldn't tell you for IN or ICN. I think there's one for IN, but I don't know about ICN.
Thank you.
And that really is why we were interested with RN in the first place, because it was conjectured to have this closed form.
I wrote down a couple of formulas.
Yeah, I think my study is going to be, I'm going to go through the chapters and write down the formulas. I think they look interesting.
Yeah, but it's like I'm looking at the homework. It's like, oh, I haven't had this problem yet. I don't have this problem.
Yeah, I'm confused as
I believe that was an incidental unmuting. Wait, could you go back one slide, please? Yes, so here you said the binomial coefficient was counting what?
The number of symmetric hook shapes.
The number of symmetric hook shapes. I thought there was only one symmetric hook shape for any n.
Yes. This number of standard Young tableau with that shape.
Okay, that's what I thought it was counting.
Yeah. Which there's just a really easy formula for that. It's the hook length formula.
Right. Classic words on two letters kind of argument, I believe. But yeah, and then what did you say the 2 to the n minus 1 over 2 was counting then?
That's counting the number of standard Young tableau that satisfy the second property.
Ah, right, because the hook shapes would kind of be your P of W's.
Yeah.
Like that's all your different ways to fill P
Yeah.
of W, and then the one on the left is all the ways to fit P of W with those restrictions.
Yeah, I
Okay.
would have flipped them, but it's kind of weird to have a binomial coefficient at the start.
Mm-hmm.
So I think you can easily see this 2 of the power because you have pairs, and then you can choose either you put it in the top row or you can put it in a column. So you have 2 to the number of pairs.
Mm-hmm.
Yeah,
Except
that's
one is a singleton, which is not paired up.
that's exactly how we show it in the paper.
The phi AB, if I act them on a permutation and then make the tableau out of them, what is the, so in this case, we're only doing it for the hook shape, right?
Mhm.
Are there general results for how the tableau will look like? Can I get all n plus 2 tableau using this? Or is there like a...
Each phi AB gives you if you apply phi AB to all of Sn, it's going to give you a partition. It's going to partition Sn plus 2. So depending on the AB, you're restricted in which shapes you get. this is pretty much the only one we saw that has a really nice relation, but there may be others. We,
So the boxes have a restriction on where they go?
yes, yeah, you have to add two to the one you started with, so to speak.
Right, so they end in like a corner.
How do you prove this? Can you use this green theorem? So
It actually, it follows, there is a result that says the number of increasing, the length of the longest increasing subsequence of entries in the permutation is the length of the top row, and the
Yeah.
length of the longest decreasing subsequence is the length of the first column. So
yeah,
since,
that's the result by green I was mentioning.
oh, yeah, sorry, I
So-
didn't remember the name of it. But since it preserves relative orders, you get that immediately.
yeah, that's what I found. Thank you.
So does, I'm not, I was unfamiliar with this theorem. Does that mean the only permutations where you get this the hook shape is if you have kind of a unimodal or reverse unimodal permutation where it goes up and then down or down then up?
No, because the sequence can be spread out. So you can have
Okay.
you can have entries of the sequences like interspersed between each other.
Okay.
I think the unimodal one does satisfy it though,
Hmm.
but you only get a couple of those.
Right. Okay. Well, if that's all of our questions, I'm going to end the recording.